Hello, everybody. Today we're starting our June session of DecisionCAMP. We run this every month so far between major events, and next DecisionCAMP will be held in September 13, 15. And by the way, you still, if you want to present, you still have chance to apply from DecisionCAMP.org website. If you want to present, it's until June 18 deadline. And today we have a quite interesting session. Dr. Bob Moore, well-known business rules engine and decision service practitioner, who spent a lot of time building real-world decisioning applications. He kindly agreed to analyze different solutions presented to decision management community challenge, where we provided one big decision table. And to do this, Bob even created something himself. And he will talk about this to be able to compare different solutions and discuss the performance of big decision tables. And without any delay, I want Bob to take over.
Okay, so good morning, good afternoon, good evening, wherever you may be. As Jacob said, the idea is I'm going to talk a little bit about performance of large decision tables. The inspiration for this was a challenge that was posted on the DMC website back in February. And the challenge was basically to implement and benchmark a decision service where the decision service is comprised of a single decision table, but it's a large one. So the challenge presents the table essentially as a CSV file, but it's got over 16,000 rows. And the idea was to build something which could be deployed as a RESTful microservice. So there are a set of test cases to run against it, which were presented in the JSON format. And a number of solutions were presented, but they are a little bit difficult to compare because you're really not comparing like for like. So exactly what the results are telling you is a little bit ambiguous. So the object of the talk is essentially to do a couple of things. First of all, to dig a bit deeper into the presented solution to try and get a bit better comparison of how they perform. And then secondly, to explore some of the issues and methods for dealing with large decision tables. But I think you can, at the end of the day, expect that I probably raise more questions than I'm providing answers. So to dig in, the challenge, as I said, is presented as essentially a set of test cases where we need to try and make a decision, and then a decision table to do that. So the test cases are in JSON format. We see that there are 7 input fields and 3 output fields. And initially we start with a JSON object, which has got 3 blank fields. And we run these through the decision table and those fields get filled in. And that's essentially the objective. We look at the decision table itself. We can see that it actually has 11 columns, there are 8 input columns and 3 output columns. Do a little bit more data analysis on the decision table. So as we said to start with, there's over 16,000 rows. These there are 8 input columns. 6 of these are categorical, so basically they're just literal values which we want to compare against. And then there are a couple of numeric values which are dates, which essentially are looking at the effective period for the particular plan. And so they're relatively limited, and they will be compared against the date that is in the input value. Little bit of math. If we actually multiply things up, then taking all of the options, we'd actually end up with a table which has got 150,000 rows. So it's a big table, but it actually represents only about 10% of the possibilities. Another thing to notice is that some of the columns have blanks in, some of them don't. That's something which we'll talk about a little bit more in a moment. So as it's presented, we aren't really given a business context. And so there are questions behind this which aren't essentially directly relevant to the challenge, but certainly relevant to understanding how we manage large decision tables. So we don't know things like whether cases are processed one at a time or in batches. We don't know what the actual performance requirements of the system are. The decision table has got various conflicts within it. So there are a number of rows where you'll find that there are identical input columns, but there are different outputs. So how are we supposed to interpret those? Now, we discussed the same challenge in a very different context last month, where Seth Meldon was presenting how one can do some analysis and compress very large tables to make them significantly smaller. And it came out that the idea of these conflicting rows was there was some concept of overrides and some concept of the table being multi-hit, but we're not given any mechanism for this within the challenge. And also the role of the blank cells is a bit ambiguous too, because some of those blank cells seem to represent values rather than blank cells in a decision table conventionally mean the value for this attribute is not relevant for this particular rule. So one needs to make some sorts of assumptions in terms of actually trying to build a solution. So the assumptions which I made, and I think other people either explicitly or implicitly made, are that we're dealing with a single hit table, and we have to do that because we've got only one position in our outputs to actually give a result. So even if we built a multi-hit table, we'd only be able to return one of the hits anyway. To assume that the blanks are values, because in our test data set, we're actually given blanks within the data set. There are explicit nulls, so we'll treat blank as a value. And we'll assume that data is provided in batches, because that's the way the test file is set up. We have our 10 test cases in a single file. Another issue which it's just worth pointing out that all of the solutions have to go through is to actually take the data and map it. So we have an input format, and we have the decision table. How do we understand how the input maps to the decision table? So this is the way it's done within the draw solution, which is presented. So we have the table column name from the CSV, and then we have the JSON input field. And for most of them, it's trivially obvious for a person to work out what the mapping is. It's a little bit more difficult for a computer, so we do need to have some explicit sort of mapping. And within draws, the mapping for the categorical data types is very straightforward. We just take we just say, you know, this is the name of the input field, this is the name of the column. For the numeric fields, we need to actually stick in some code fragments to actually explicitly say what the test is that we're doing. And for the action fields, we also need to put in a bit of explicit code to essentially say, well, if the rule matches, then this is what we write into the output stream. So the next slide shows essentially what the performance results as they were given on the website. I've made some subtle adjustments to these to get them a little bit more like for like, but there are still some issues with that. So if we start off with the first line, the prologue solution that was provided by Matteo, the time which he gives, which is 1 millisecond, is actually the time per case, but it includes the network time. So this is the time from the client calling the service to it being taken over to the server to be processed and then returning. Whereas all the other times are actually internal times, the times which are actually spent on the server itself. then the other solutions which have been asterisked, what we're actually given is not the time to process a single case, but the time to process the whole of the input file. So I've divided all those by 10 to get things down to a time per case. But we can see that there is a big range of values ranging from tens of milliseconds to process a case down to tens of microseconds. So there is a big range here, and we'll sort of explore a little bit more detail as to why that may be later on. So in order to try and at least get some better handle on how to compare things, what I took the solutions which had been implemented as Docker containers, because what I could do is essentially take those Docker containers, put them all on the same machine, which in this particular case is my old laptop, which is sitting next to the one that we have the Zoom session on, and essentially then perform tests against that. And that would give me essentially like for like, because I know everything's running on the same operating system, on the same hardware. So the response times I can directly compare and say, this one is sort of, operating 2 or 3 times faster than that one or whatever. So the first set of results, which are shown here, are the tests where we include the network time. So this is the time taken for my laptop to send a message across my local area network to my other laptop, for that message to be received by the decision service, the JSON to be parsed, the rules to be executed, the results to be copied back into a JSON message, which is sent back to the client. And the top row basically shows us what happens when we take the test case as it was provided within the challenge. We executed 100 times on the server to get some, to sort of even out some of the network delays and so on. And we can see that typically we're getting response times from all of these systems of around about a millisecond per case. Now, what I thought is, well, if we're sending things in batches, then what happens if we send larger batches? So I wrote a noddy little program which picked rows at random from the decision table and then created test cases which would match against those rows. So I built up a file which had got 100 test cases, 1,000 test cases, and 10,000 test cases, and tried running those against the same services. And what we can see immediately, particularly if we just look at the difference between 10 and 100, there's a dramatic improvement in the performance, because what we're doing essentially is we're taking away the network latency issues, and so there's a big shift away from most of the time being spent actually making the network call to more of the time being spent on the server. But as we'll see on the next slide, there's still quite a lot of time being spent in the network traffic, and it's interesting to see here that not only we improving the time per case, but if we actually sort of think in terms of bulk, how long does it take to process 1 million cases? Well, for all of these systems, and I mean, taking the worst case scenario, which is from this set of runs was actually on open rules, that's taking less than 3 seconds to process 10,000 cases. So that's less than 5 minutes to process 1 million cases. The next slide looks at the three of the Docker solutions which actually allow us to get internal time. So we can essentially work out how much time is being spent on the server processing the cases. And here again, we've done it with 10 cases, 100 cases, 1,000 cases, and 10,000 cases. And we see that the processing that's actually taking place on each of these systems is of the order of a few tens of microseconds to process each case. You'll notice that on the website, Jacob's open rule solution is faster, is the fastest, but he obviously has a faster processor on his machine than on mine, because it wasn't the fastest on my machine. But I think the thing is that it doesn't really matter too much. The key thing is that all of these solutions are providing really quite fast responses to individual cases. So if we want to process very large bulks, then using something like open rules or rules is going to be a very effective way of doing things. I'm not suggesting that you use the custom solution. It's something which I put together quite quickly, and it's certainly in its current form, it's not particularly robust. Now I've glossed a bit over how the performance testing is done, but as suggested in the challenge, I used Postman. Postman is very good for testing APIs from a functional perspective. So when you make the calls, it will validate that the services are performing correctly, but it's not as it's designed set up to do performance measurements, but it actually turns out to be quite easy to add performance measurement into that. And so I'll just do a quick demo of the sorts of things that we can see. So I have a bit of a problem because I've got the gallery is using up some of my screen, but I will shrink things down a little bit. So if we look down here, we have a number of messages which we can send to each of the Docker containers. So for example, I can just sort of send a message to Matteo's Prolog container. It'll go away and it'll come back. And we get a response time. The response time here, typically the first time I call it, you get quite a long response time. If I kind of run it several times, you'll see that the response time drops down. But if I say go to here with rules here, what I've essentially set things up to do is to say, okay, I'd like to execute this query, but after I've done that, I'd like to run some JavaScript. And when I do that, then I can actually have a quite complex script here, and it's relatively easy to set up to say, okay, having done the call once, I'd like to do it another 100 times. And each time you do it, I'd like you to gather the performance statistics for that call. So then within the call, in this particular case, we can see that in addition to the results fields down here, I've got some statistics about how things happen. So for the rules case, I have 4 separate timings. One is for essentially selecting the decision table, then one for parsing the input, for actually processing the rules, and then for writing the output. And when I finished executing this, if I go and have a look in the console, then I will get, when I get down to the bottom, I will get essentially individual timings for all these things. And also the script actually does the stats for me as well. So it'll work out the mean response time, which in this case was 20 milliseconds. And there's the standard deviation, the minimum, the maximum, and so on. We see that generally there is a big variance between the minimum and the maximum time, but also it gives me the information for the individual timing characteristics as well, which is essentially how the statistics tables, which I was showing you earlier on, are built up. And obviously we can also do this sort of thing if we have a Lambda implementation running on AWS or something like that. Okay, so I've talked enough about the solutions and the challenges, take a step back now and actually sort of think a little bit about the challenges of the big decision tables. And I mean, I think there are a number of them. The sorts of things which struck me, particularly while looking through this and also remembering things I've done in the past, were, well, first of all, if you've got a large table, it's very hard to understand. No one is going to understand all of the ins and outs of the 16,000 row decision table. People will have a fairly good, there will be a number of people who have a fairly good idea of what's going on in there, but nobody's going to know everything. The other thing is that they tend to turn up essentially in a kind of legacy way. So you will have, as the challenge indicates, customers who turn up with typically a very big database table, which they then want to convert into some sort of decision service technology. And when they're doing that, they don't always ask themselves the question as to, is this actually the right way to be solving the business problem that we have? What exactly is the relevance of that? Do we need to do some tidying up of what we've got? And sometimes they don't even ask themselves the question as to whether a decision table is actually a best solution to the problem. Those of you who've looked at some of the solutions I've provided to other challenges will know that I have I do tend to have to come up with solutions which actually don't go for decision tables, but use more of a kind of object and rule based approach. And I find that in a lot of cases that actually works as a better way of doing things, better in the sense that it makes it easier for the business to actually understand what they're doing, and more flexible in terms of different sorts of things that you can do. Another issue can be that the decision table doesn't become the source of truth. The source of truth is somewhere else. And so what you actually need to do is take whatever your source of truth is, which might be the CSV file, more likely is some sort of database table. It might be a book with lots of tables in it, and take that and use that to build a decision table. But how do we maintain the table as it evolves over time? And also, how do we test and verify this new implementation of the logic? If you've got a decision table that's got 16,000 rows in, testing it is going to be a challenge. And finally, it's worth getting the business to actually consider the question of, is performance an issue? Simply because you've got a decision table that's got 16,000 rows doesn't mean to say that you actually use it very often. So if you're not using it very often, then the performance of it doesn't actually matter very much. And you may be thinking about putting a lot of effort into doing something which isn't actually very important. So are we calling this thing once an hour, once a minute, several times a second? What's our required throughput? I mean, are we trying to process 10 cases, 100 cases, 1,000 cases, 1 million cases? And what's our batch size? As I said up front, we don't know the answer to that question. But obviously, if we have large batches, then we typically can process those somewhat more efficiently. But it may be that actually only makes sense to process batches of size 10 or 15. So, do we actually have batches which are very big? Once we've actually answered the business questions, we then can go on and start thinking about the technology questions in terms of how do we actually try and build a solution which is efficient. And obviously, the efficiency is how quickly we can match the inputs with the table rows. Pradeep provided a custom Java solution, which, when you actually look at the sort of performance, it doesn't perform too badly. But if you compare it against the optimized solutions, it's still the best part of a couple of orders of magnitude slower. And that's because his solution is straightforward to implement, but it uses linear search for the tables. And linear search just doesn't work if you have lots of rows. Few rows, it's actually quite efficient, but it becomes inadequate if you have lots of rows. And remember working on a project about 25 years ago where we were using a product which was using linear search, and we had all sorts of problems with it because we were just trying to get it to tackle a problem that was too big for linear search. But one of the things in our favor is that big decision tables tend to be quite simple. So we have categorical data where most of the time we're doing equality tests. And if we have numeric values, then we're typically doing fairly simple sort of range tests. And typically we'll only have one kind of test per column. So while we need efficient search strategies, there is no shortage of work in those sorts of areas. So if, for example, we look at databases, they've been trying to do these sorts of searches for a very long time. So there's decades of work gone into how to efficiently search systems. Typically, the mechanism that's used is B-trees, which, as I understand from Jacob's solution, is the primary process that was being used in the Open Rules Big Table facility. You can use hashing, which I kind of use as a roll your own solution. It's got limited functionality, but it did turn out to be the fastest in the challenges in terms of actually processing things. Caching is an overlooked mechanism, I think. Rob Parker used it in his solution, which gave him a significant speed up. But the point is that although, again, if you have a decision table that's got 16,000 rows in, it's quite often the case that of those 16,000 rows, 15,500 of them only get used once a year. And so if you focus your performance optimization on the 500 rows which are frequently used, and you can use some sort of caching mechanism or optimization mechanism for those, you can get much better performance. RETI-based algorithms obviously are very, very suited to this as well. So this is why Drools has an excellent performance, because the way it's processing the rules is based around a RETI-based algorithm. And although Prolog is notionally not the fastest thing on the planet, for this particular kind of problem, the idea of the way it does unification means that a reasonable Prolog program will actually perform very well in terms of solving this kind of thing. Okay, so that's really all I have to say from a kind of formal presentation perspective. And what I'd really like to do now is to open things up so people can discuss ideas. I'm certainly willing to try and answer questions, but I think there are probably people have their own ideas, which I think would be useful to discuss among ourselves.
Yes, thank you, Bob. It's certainly very interesting. You can talk more about this, I'm sure, like we exchange few emails.
Yeah.
Okay, let's take questions from everybody. Just unmute yourself and talk. Any questions?
Hey, Bob. Thanks a lot for the presentation. It clarifies a lot of things. Actually, we've been recently into Drools as an organization. I work for a company called Zeta in India, and we just load tested Drools a couple of days back on our production service, and it turned out to be really good. And thanks a lot for your help in that area. We had a look at your detailed documentation in the DecisionCAMP website, so that is a lot more useful. But I'll be much more happier if Dr. Bob and Jacob, if you could spend some time on telling us about the differences in the machine that you were using for testing.
Well, I think I can't. To be honest, I can't remember what the spec of. But I mean, my old laptop is basically a generation 6, I think, i7 processor, and it's got 8 gig of memory. So I mean, when I got it, it was a relatively high spec machine, but that was about 5 years ago. From the performance that I've seen when deploying the solution as a Lambda function on AWS, I would say that it's a little bit faster than the sorts of thing that you'll get by default from an AWS server. I'm using a free AWS account, so I'm not expecting to get anything dramatically powerful. But the problem I found with Drools is that the documentation is a bit sketchy on how you actually know which bits are actually important and which bits are not. And so you end up with something which looks as if it's got an awful lot of fat in terms of when you do things like the deployment. And it's a bit difficult, to sort of see how you might trim that back down. But I think the thing is that the performance that you seem to be getting out of it is probably as good as you're going to get, and so it's really more a matter of if you can get better hardware. One of the points that I haven't sort of really mentioned here, but I make a big point of in my submission, is that when you're looking at a solution, if you're worried about performance, the first things you should be thinking about is, well, what am I actually trying to deploy this on? So if I'm putting this out to somebody like Amazon to provide the services, what are my network delays going to be, and what sort of hardware am I going to be running if I'm deploying to the cloud? Because no matter how good your algorithm is, if your network is too slow, and if the server's only giving you a very slow processor to process things on, you're not going to get dramatic responses. But from a practical perspective, if you're dealing with if you can't bulk up your courses, so if you can't create batches as I did in my testing, and Jacob also did in his, then you're always going to find that actually the network time is something like 2/3 or more of the time that the client sees. So if you're looking at the end-to-end processing, network delays substantially have a substantial effect on it. So ideally what you want to do is try and ship a large amount of work to the server, so the time that you're waiting for the message to travel across the ether becomes smaller compared to the overall response.
I can add few comments about performance. I completely agree with Bob that everything depends. Networking time could really suppress all advantages of rule engine. But let's consider opposite case, what we started to face approximately 3 years ago, when our customers who used to handle millions of transactions per day, and they were happy with performance like 50 milliseconds, 100 milliseconds, it was okay with them. But suddenly they started to tell us that they need to billions transactions per day. And this it brings us to new quality, it's not anymore quantity, it's new quality of engine. And that's why approximately at the same time, Open Rules and Rules, we together moved to new implementation, completely new implementation. It's reflection free, right? Nothing in runtime, only everything is designed. And for us, each transaction, even if you perform this, forget about networking for a second, when you perform this in pure Java API, what maximum performance we can reach. And that was another reason why, for example, we implemented this big table special algorithm for this, because this was crucial And when we saw performance improvements, especially for large tables in the order of 100 times, that was something what was really important. And what is interesting is that two open source products, Rules and Open Rules, we did this in parallel without talking to each. We had some discussions during decision camps, but not about algorithms. And it certainly paid off for both of us, as you can see from this example. But I want to make one more important point, what Bob said about batches. What size of batches? This is our customers. They tell that they want to control this based on their situation, and they want to control this programmatically. So they want to accumulate different requests in batches and send them. And then, like Bob demonstrated, this it could be extremely powerful batching mechanism that what we'll do. So this is a good exercise, but certainly example of table was not so good. We really, and unfortunately we cannot share our customer data. If somebody can, it would be great if you send this to DM community, and maybe we can have another benchmark.
Got a question. This is Rob in the United States with InRule Technology. Thanks for having me on. Just kind of curious. I know the constraints of the exercise asked about one decision table, but Dr. Bob, you had mentioned the possibility of finding a way to kind of narrow the top of the funnel, perhaps with some sort of extracting some of that logic into a separate piece of logic prior to the decision table. One of the things we do when we're working with customers in a scenario like this is we'll oftentimes try and have one decision table that'll account for the majority of at least one of the use cases or one of the primary use cases, and then have the outputs of that decision table be inputs to the next decision table. Is that something that you all would consider as a way of kind of improving performance, trying to kind of account for the most common use cases in a smaller decision table and reserve the larger one for the for the less common use cases?
I would certainly do that. I mean, the thing is that as I think Jacob has said, and certainly I tried to put across in my presentation, is this is a slightly artificial example. Right? It's a very artificial example, to be honest. And so what we're doing here is a small part of what should always be a big problem. And what I hope I try to emphasize is the performance is the second question you ask. The first question is, what's the business problem? And to try and understand that. And there are not going to be all that many decision services which actually comprise of a single table. Typically, you are going to have, you're expecting to do, there'll be more than one stage in the processing. And so the idea of essentially trying to do things like caching or do things like essentially understanding from a business level the way that the table is worked are very important in terms of trying to optimize performance. And the idea of essentially saying, let's pick out the cases, because I mean, I mean, this is obviously some kind of medical insurance example, and I mean, when I've looked at, I was involved with a system like this many years ago, and you would find, okay, there are certain sorts of things like you're doing blood tests, you're doing things like observations of blood pressure, heart rate, oxygen saturation, and so on. Those you're doing all the time. So if you actually kind of take those, they're going to outnumber everything else by 10 to 1. So if you have a bit of logic which pulls all of those out of the things that you're processes those separately in a very efficient mechanism, then the fact that whatever else you have may or may not be very efficient doesn't matter so much, because you've already taken away most of the work in something which is highly optimized. So it is it is something that's important. And again, one of the reasons why I was kind of making the point about batches was in this other system that I worked on a while ago. The batches had a definition because basically they were an insurance claim, and so most insurance claims would consist of maybe 3 or 4 items, but some of them would comprise thousands of items because they were claims associated with long stays in hospital. So you'd have to kind of find some way of sticking together multiple claims into larger batches if you wanted to get the sort of optimization of the network latencies. So there are a number of different things that come into play there, but certainly the idea of optimizing things by saying, okay, that we know that these cases, I mean, it could be 10 or 100 account for sort of 70 or 80% of what we're doing. Then if we focus attention on those, we're obviously going to get better performance.
I was as a corollary to that, we're in the middle of transitioning to an AI acquisition that we have as well, and I would absolutely consider the possibility of training some AI to look at the batches and see if that can help us retroactively make the tables themselves more efficient by understanding where the majority of the claims would come in.
Rob, yeah, that's good. I just want to add that today we are in this serverless world where we have not one but multiple decision services. And if previously we considered splitting large tables in multiple tables, that was a good option, and each table could be well designed. What usually Jan says, if you design each table properly, it would be completed, it would not have conflicts. But similar architectural approach is valid today when we consider not one but multiple services, and then we have service orchestrations logic or choreography logic. This becomes what I want to make a point. It's still our territory. It doesn't belong to AWS or other network vendors. They provide nice steps function and logic with state machines, but business logic, how to invoke different services, it's a business logic, and it could be presented in another decision table. They tell you how in optimal way to invoke different services. So we can have really decision microservices. Each of them could be highly efficient, and combining them based on analysis of your particular problem could bring a lot of efficiency improvements. Okay. More questions? Maybe just while we're on this topic, I just want to tell you a little bit more about this particular problem, where it comes from real world. Unfortunately, this is such decision tables, they keep to grow, like everybody experiences. And in real world, people give access to this logic to business people. They give them copy-paste facilities, and 5, 10, 15 different people started to add these columns, like in this 16,000, this in real world, it could be 30,000 rows, and they all could be in conflicts, and people use it. It's not regular lookup. People can use multi-hit tables with a lot of rules overrides. They can accumulate multiple results, and another table can compare them and select the best one. So it's not always possible to split a big decision table in multiple tables because historical logic. So we should start looking on these microservices. It's much better definition than the word decision table or any other traditional construct. And DMM defines this quite well, what the modern decision service stands for. Okay, any other comments, questions?
I don't have a question, just a comment. If you're working on such large decision tables, of course, it shows that there is a problem in the business. And of course, you can execute it very
Jan, you're very faint. I can hardly hear you.
Very faint.
Yeah.
I hope you can hear me.
Oh, yes, that's better.
Okay. Working with 16,000 rules or rows is of course a problem. No matter if or how efficient you can execute it, it's a nightmare for maintenance, I think, to keep track of 16,000 rules. So there is a big problem coming in this decision table or the set of decision tables, and I think that is the real problem.
Yeah, I agree entirely. I think I mean the way I would be wanting to sort of look at it would be asking questions like, you know, what are your objectives? So within the decision table, I mean, what I sort of thought when I looked at it was, well, I've got these things called plans. Plans presumably are things which we sell to customers. So should we be trying to organize these things around the plans in some way? And I mean, I don't, you know, I mean, this is all speculation because as we've kind of discussed, we don't know the business context. I mean, Jacob does, but he can't really share it with us. But I think the thing is, if you take something like a big decision table, then the sort of thing you'd be wanting to do would be to look at it and try and pick out, you know, what is this decision table for? I mean, the business have some reason for having it. So what are those objectives, and are there some ways that we can actually understand the table in the context of the business objectives and use the business objectives to help us actually build a table in a better sort of way, and optimize what's going on. And you know, the sort of question I was asking, well, I've got, I can't remember, it's 21 plans or something. What's the difference between these 21 plans? Why is the, you know, why do I have 21 plans? What are these 21 plans doing that's different for me in these different sorts of circumstances? Can I take advantage of that? And I think the idea that we could use something like so some sort of AI tools to do things like cluster analysis and so on the table, it might actually be able to pull out some of those ideas. But at the end of the day, the business came up with it in the first place, so they must be able to give us some hints as to how this thing turned out this way. It's but I mean, those are the questions I'd be asking.
I think very often such a large table is some kind of translation of a continuous function to breakpoints.
Well, it could be in some cases, but for example, I did some work for a steel company once upon a time, and they basically had, I mean, there are hundreds of different sorts of steel, and they had hundreds of clients who each had different sorts of requirements in terms of what they would want to do. So you'd have essentially these vast batches of rules, which would essentially work out how to match the order which came in from the client, using things like client rules and using things like production rules to come out with how do I actually create a work order for the steel mill to actually produce the right sort of steel. And those essentially kind of end up as being very big decision tables. But the thing is that you can actually, because you can see the process by how you got there, it actually then becomes much easier to make sense of the tables. And even though they are big, because you can go back and say, well, we know that, you know, these things are here because the physical apparatus within the steelworks says that we can only do these things. And we have each customer, and we can say separately for each customer, this is what this customer wants to do, independently of the other customers. And we end up with a whole load of data, but we know where it all goes and where it all, you know, where it all comes from, where it's all going. And so it becomes a more straightforward sort of process in that kind of environment. It's a lot of data, but it's been well organized.
Yeah, there is a reason. Thanks,
Okay.
thanks for your good presentation, by the way.
Okay, thank you, everybody. If no questions anymore, in this case, just for conclusion, I really want to thank you, Bob. I read, like I told you, his submission as a detective story. It was really fun, and he did, this is what he calls custom simple engine. He did magnificent job reproducing what majority of big vendors or open source vendors created already. And this is quite, thank you, Bob, a lot. And I also want to invite everybody, and in particular some new people here, to volunteer for next presentation for DecisionCAMP. Rob, you just mentioned the acquisition of AI company by Enroll. So it would be interesting to see if you want to, together with your new company, present some topic about AI and business rules. A combination could be very interesting. And again, we have DecisionCAMP in September, and June 18 is the deadline. So please don't miss this deadline and send the abstract of your presentation, decisioncamp.com. You will find there, and thank you everybody for participating, and you will find the recording on the website. Thank you. See you next time.
Hey, thank you. Thank you very much.
Bye, Jacob.
Thank you all.
Really insightful. Thank you.
Thanks.
Thank you.
Thank you.
Bye.